Hi everyone, welcome back to Grade 10 Maths with Mr. Simons, where we make maths simple and we get you exam ready. Right, in today's lesson we're looking at trigonometry in 2D. Yeah, this is just to explain to you and show you where trig ratios come from before we look at lessons of past exam questions on it. Right, so let's go to the first slide. So now, that ratios that I did in a previous lesson by telling you that sine theta is opposite of hypotenuse, etc., they weren't just randomly created, right? They actually originated from studying the geometry of right angle triangles, meaning that angle or triangle we draw always has one right angle in it, and we pre-decide how big we're going to make the other angle. Right? So in astronomy, surveying, architecture, there's a lot of right angle triangles. If you go look in your room, you'll see each corner there is a 90-degree angle, right? And that later on, if you go into architecture and so on, will relate to stress and strain of building, steel structure, etc. But the key is one angle is always 90 degree, and the other two angles will then be acute angles, angles that are less than 90. Remember, the three angles can only add up to 180. So technically, if this one is 90, these two can't be 90 or more. So there, if we worked from theta, opposite, adjacent, hypotenuse. If I worked from beta there, then this would become opposite, and that would become adjacent, but the hypotenuse is still across the 90 degree. So the ratios between the sides stay the same for the same angle, no matter how big or small the triangle is. Right, so what I technically mean is I can make these lines a lot longer, but still ensure that this angle is 30 degrees, and then check the measurements and lengths of these and how the lengths relate to each other in ratio form. So let's look at the next slide to show you what I mean. So the big idea, ratio not technically equal to size. So let's say we have an angle 30 degrees. You see they have a small triangle 30 degrees, a bigger angle 30 degrees. Whether the triangle is tiny or massive, the proportion between the opposite, adjacent, and hypotenuse side will always be the same. Right? So in short, what I'm saying is, if we create a 30-degree angle, doesn't matter how big we make the triangle. If one is 90, at angle 30, remember the remaining angle can only be 60. Ne? So what we have discovered then by doing this is that the sine of 30 degrees will always be 0,5. That means the opposite side is always half the hypotenuse, no matter the triangle size. So there, that's 30, and we draw a side there that's 3, right? For that to be 90 and this to be 30, then this side will be 6. It will always be double that, 3 over 6, opposite over hypotenuse, to give me 0,5. If this is 30, yeah, and the opposite side is 5, then this must be 10, because the sine of 30 is opposite of hypotenuse and must always give me a value of 1 over 2. Does that make sense? I hope you follow. Right, so by studying this right angle triangles and substituting these angles in there, they discover those three basic trig ratios that say SOHCAHTOA. That sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is always opposite over adjacent. And that the ratios and the values the ratio will always be the same, although the sizes are different. So it's like doing equivalent fractions where we say 3 over 6 is the same as 1 over 2. Am I making sense? If not, I'll leave a comment and so on, and I will see if I can explain it for you further. But let's go to the next slide. So ancient mathematicians, yeah, you like to call us ancient just because we're older than you, but yeah, right, they noticed the patterns. So ancient Greek mathematicians, Hipparchus, Ptolemy, and later our Indian mathematicians like Aryabhata studied right angle triangles by drawing them inside circles. They measured angles and side lengths and recorded the constant ratio between them for each angles. So you see what they've done? They measured the angles and the side lengths and worked out the ratio for them over and over. I know it's something you won't do, but yeah, in real maths we have to do this to prove that something is valid. Right? So these constant patterns led to defining my trig ratio, meaning so sine in short tells us how tall the triangle is for a given hypotenuse. Cosine technically in ancient maths was used to tell us how wide a triangle is, and the tangent, which I said to you previously in the previous lesson, means gradient, is how steep it is. So sine, written in short as sin, not sin. It comes from the Latin word sinus, meaning curve, right? And it's related to how the opposite side rises like a wave, right? But that's, yeah, we'll do when we do trig functions. Cosine literally means complement of sine. That's why it's cosine, right? Or in short, we say cos, right? So cosine is the complementary angle. So what I mean with complementary angle, if sine is 40 degrees, then cos there on the other side must be 50, because 50 plus 40 gives me 90. So two angles add up to 90. They are referred to as complementary angles. I hope that makes sense to you. Tangent comes from the Latin tangens, meaning touching, and originally referred to a line touches, where a line touches another curve, right? So it comes from the Latin word tangent. Yeah, some of you would find this boring, but I'm explaining so you fully understand. But yeah, let's conclude it with the next slide. So concept trig ratios. They describe how sides of a right angle triangle relate to one another depending on the angle. Origin, it's discovered by observing consistent ratios for each angle. And the reason why they work, because the triangles with the same angles are similar. Their sides are always in the same proportion. They're always in either 1 to 2 or 2 to 3, etc. Right? So we look at the real world example. You are getting ready to install, say, a satellite. Right? And you install your ladder looking up and forming a 60-degree angle with the ground. Right? So if you know what this distance is and you know how long your ladder is, you can actually work out the height of the building without taking a tape measure. Alright? Same goes if you have the height where your ladder stops, you know the length of the ladder, you can work out this distance there. So in short, you don't need to measure anything, just use 3 cos 60 equal adjacent over hypotenuse, which tells you how far the ladder reaches horizontally based on its length. Something that pipe fitters use regularly, right? So pipe fitters would work out if they don't have measuring tape and so on, where they have to cut the pipe so that they can put a proper L joint, etc. in here. But that's just real world examples. So whenever you're going to do in construction, you're going to work with a lot of right angle triangles and placing things at 30, 45, 60, etc. degrees to work on them. All right. I hope the lesson was useful. If you found the lesson helpful, you like it, please like and subscribe so you don't miss the next lesson. Wish you nothing but the best. Continue practicing. Bye.